Hey guys, today's video will be on Graham's law and Maxwell-Boltzmann distribution curves. So the first thing I want to talk about is that temperature is really just a reflection of motion, right? So if we're investigating a sample of gas, what we're really describing with temperature is just the degree of motion. And the idea is that with higher temperatures, we are going to have greater motion, okay? If we go back to the kinetic molecular theory, okay, one of the results of the kinetic molecular theory is that the total kinetic energy of a mole of any gas is equal to 3/2 RT, where R again is the universal gas constant. Okay, so we can say the average kinetic energy is equal to 3/2 RT. If we kind of, to some degree, eliminate the 3/2 in the R, we can just say that average kinetic energy is proportional to temperature. So if we know the temperature, we can talk about kinetic energy. That being said, if we know the kinetic energy is equal to 1/2 mv squared, this is really useful all of a sudden, right? Because we can now equate temperature with the mass and speed of a gas sample, okay? So if we actually take a look at these two equations here, we can actually set 1/2 mv squared as being equal to 3/2 RT. And with some rearranging, we can solve for velocities being equal to the square root of 3RT over m, where this m is like a large kind of cursive m, kind of historically written. It stands for molar mass. Now in our specific equation here, the units of molar mass will be in kilograms per mole, given the units I've used for the universal gas constant. This is a little bit different than what we're accustomed to, this 8.3145 joules per Kelvin mole. And I'll leave the derivation to you guys, but remember obviously that our temperature is going to be measured in Kelvin. And that another way that we can express joules is kilogram meter squared over second squared. So if we look to eliminate some of our units all of a sudden, we can actually be left with velocity. By the time we eliminate these units, we can arrive at meters squared. So again, the kinetic molecular theory isn't just something that allows us to talk about the behavior of gases kind of conceptually. We can also use it towards describing relationships as far as temperature, again, kinetic energy, and then ultimately, for our purposes, we're going to discuss a lot of things concerning mass and speed of these gas particles. Okay. So let's get into the idea of a Maxwell-Boltzmann distribution curve. Let's say we're taking a look at a sample of nitrogen gas, okay, where the molar mass of nitrogen gas, 28.02 grams per mole. Again, if temperature is proportional to the average kinetic energy, we can begin to equate temperature with velocity, okay? And so what we find here is that at lower temperatures, we're going to have most of our gas molecules be of relatively low molecular speed. As we look to increase the temperature, say from 300 Kelvin up to 700 Kelvin, again, a lot of our gas molecules are up towards 1,000 meters per second there. Okay, what you'll notice is that the area under this curve is representative of the total number of molecules. Whenever we have a sample of gas at a really low temperature, a lot of times that distribution curve is going to be pretty tall and narrow, where we don't have this really large kind of diversity or a large range in the motion of those gas molecules. Okay, some are moving maybe quite slow, and the upper extremity is not all that great. But as the average kinetic energy increases, say up to 700, now all of a sudden there's a larger number of gas molecules that have the ability to exist at these larger molecular speeds, and so we see this extremity kind of broaden out a little bit. Okay, this becomes a little bit flatter in nature, this curve there. Okay, and these Maxwell-Boltzmann distribution curves are nice if we want to evaluate, say, a single gas at multiple temperatures. But the question kind of becomes, what if we want to start comparing two different gases? And now we're going to get into a discussion of Graham's law of diffusion. At the same temperature, if we are talking about two different gases, okay, say gas A and gas B, we know that their average kinetic energies will be equal. Okay, again, through some clever derivation, which I'll leave up to you guys, it's kind of a laboratory and class exercise, we find that the average speed of gas A and B is inversely proportional to the square root of their respective molar masses. So up here in the numerator, while we have the, say, velocity for gas A, we notice that on the other side of this equality, we actually have the molar mass of B in our numerator there, okay? Bottom line is, if we were to plug in some numbers, and I think intuitively this makes sense, at a given temperature, lighter molecules are going to move faster on the average. Okay, so again, if you have a gas that has a low molar mass, we would say that this has a faster, again on average, molecular speed. Okay, let's revisit these Maxwell-Boltzmann distribution curves for a moment here. And let's try to not just say evaluate one gas at a range of temperatures, but what if we were to take a look at a scenario where we're given three different gases, say molecular chlorine, molecular nitrogen, and helium here, all at the same temperature, right? So in this case, 300 Kelvin. The idea is that because they all have different molar masses, again, if temperature is proportional to kinetic energy, which is equal to 1/2 mv squared, when we find, say, in the case of chlorine, if the mass increases, well, in order to maintain the same amount of kinetic energy, we're going to find that the velocity must therefore decrease, right? It's an inverse relationship. As one increases, the other must decrease. And so, again, for heavier gases like chlorine, the average molecular speed, not so great. Okay, but as we progress to the right on this graph here, and we get to something like helium, which has a really low molar mass relative to, say, nitrogen or chlorine, as its mass begins to decrease, right, as the mass decreases, because it has so much inherent kinetic energy in the sample, we actually find that then this velocity term has the ability to increase significantly, right? And so we see a huge portion of our sample, kind of shifting over to the right here, where all of a sudden a bulk of these helium atoms have quite a large molecular speed. Okay. Now our goal is to, in the following lab, in the Graham's law of diffusion lab, is we want to validate that Graham's law holds up, right? That the math checks out. Okay. So the way the lab exercise is going to work is that we have these long cylindric glass tubes, and on one end we're going to just dab a little bit of cotton into a aqueous sample of concentrated hydrochloric acid. On the other side, dab a little bit of cotton to an aqueous sample of ammonia. Okay. Now these are solutions, but those gases have the ability to evolve out of solution. Really, hydrochloric acid is just HCl. It's a gas that's been dissolved in water. Same thing with ammonia, just a gas that's been dissolved in water. Okay. Now, once these are kind of contained within the glass tube, some of this HCl gas is going to start diffusing off to the right. Some of this ammonia gas is going to start diffusing to the left. They will eventually meet, and as that happens, we will be able to visually observe that as far as almost like a cloud. We can call it a smoke ring, but it's literally where we are forming ammonium chloride. Okay, it's almost going to look like a precipitate is forming in thin air. Now, knowing the distance that HCl has traveled and the distance that NH3 has traveled, we can just go back to kinematics from physics last year, and we can calculate their individual velocities, right? So I know per some time frame how quickly HCl was moving and how quickly NH3 was moving. And knowing their velocities, we can use Graham's law, right? We can calculate their molar masses, and we can figure out what, hypothetically or theoretically the velocities should be, right? And so this would be kind of our known right, per the Graham's law equation. And then we can actually do an error analysis, right? We'll be able to find the percentage error based on our own numbers, okay? Thanks for listening, guys. Take care. Bye.